So thank you very much.
Good.
So I would like to present an experiment with a quantum machine that exhibits both energy efficiency and quantum advantage. And before I start, I would like to give a simplified definition of quantum thermodynamics. So let's assume we have a system which is described by a density matrix. And I would claim that what we teach students, conventional thermodynamics, is the thermodynamics of the diagonal matrix elements. And I hope you all agree with that. I see Felix in the first row. And then we now move to quantum thermodynamics. In that case, we might have some coherences, some off-diagonal matrix elements, and I would define quantum thermodynamics as the thermodynamics that involves the diagonal and the off-diagonal matrix elements. Now, what you see here is one of the very first heat engines. And I would also claim that the heat-to-work conversion is one of the big discoveries that started thermodynamics, and this is a pillar of the classical version of it. And what you see here on the right-hand side is a sketch of a quantum machine, a two-level system, two reservoirs. And now we might play with the off-diagonal matrix elements. So if we have a heat-to-work conversion mechanisms, you only play along the diagonal. And if you allow for coherence-to-work conversion, meaning you combine the off-diagonal and the diagonal matrix elements, this is something that you could consider as a paradigm of quantum thermodynamics. And the experiment I'm going to present is going to play at that level. So the two main issues I would like to address is, the first one is quantum advantage. We want to build quantum machines. I mean, that's fine. But they're only useful, one of the usefulness, or the hope, let's say, is we can do better than using classical machines. So that's one simplified definition of quantum advantage. And I would like to combine this with energy efficiency, which I'm going to define by saying that we get more output based using a similar output. You use the resources that are available to us in a slightly better way. So that's energy efficiency. And to do that, I'm going to consider a standard four-stroke heat engine. So if you don't drive diesel or an electric car, you're going to drive an Otto cycle. So this is what you see here is the mean energy of a system, harmonic oscillator, a qubit, whatever. And then we see 4 different steps. When you change the frequency of that system, you have compression, heating, expansion, and cooling. And by doing that, you close your cycle, and you can restart again. So again, this is what we teach students. It's not a PV diagram, but it looks very much like that. The experimental platform that they're going to present is a trapped ion system. And the experiment was actually done in the group of Yiheng Lin at USTC in Hefei. So that's the basis of the talk. What you see here now is a sketch of the experiment. You recognize here the two-level system, which is going to be the working medium of my machine. This is going to be coupled to a hot reservoir and to a cold reservoir. The two of them are implemented using some optical pumping techniques. At the same time, the engine is coupled to an external battery, which stores the produced work. And what you see here, this is a harmonic oscillator, and what you see here is a device which allows to measure the energy contained or stored in that battery. So the first question I'm going to ask, would like to answer actually, is how to detect quantum features. So you have a quantum machine in the box. The experimentalist tells you it's a quantum machine. How can you tell? One way to tell is to open the box and look inside, but then it's going to behave classically. It's the same problem as with the Schrödinger cat experiment. So this is not something that you like to do. You want to keep the box closed, and still you want to be able to detect quantum features. So one theoretical proposal is not to measure the qubit, because if you measure the qubit, you're going to destroy all quantumness, all off-diagonal matrix elements. So the proposal was, hey, let's just measure the energy which is stored in the battery, and do that stroboscopically. So you start your engine, let it run, and then you measure, wait, and measure again. And the theoretical prediction by some colleagues is, if you have a quantum system, and if you have intercycle coherences between the first, the second, the third, and the nth cycle, one should see oscillations in the work output. So that's something that you know from quantum beatings. You see oscillations, it has to be quantum. Before doing that, I'm going to have one slide about theory. I need to show you, I'm a theorist, so I have to show you some Hamiltonian at some point. What you see here is the Hamiltonian of the machine, of the engine. So this is the two-level system. Sigma x is one of the Pauli matrices. Omega is the frequency of that qubit. And then you applied some external driving, which is controlled by this parameter v of t perpendicular to it. So sigma z is the z Pauli matrix. So coherence is supposed to be always good, but this is not the case. Because if you do it wrong, you induce coherences in the basis of the qubit. That's fine. But creating coherence, if you don't have it in the first place, costs energy. And the energy that you lose leads to something that people call quantum friction. This leads to energy dissipation. And this happens if you have very fast driving and when you induce non-adiabatic transitions. So if you drive very slowly and start in a given energy eigenstate, you stay there while you change the energy of your level. If you drive quickly, you induce transitions, and these transitions is energy that you lose. So this is quantum friction. And quantum friction, as the name indicates, is bad. Everything which leads to friction leads to dissipative losses, irreversible losses, and then you expect your machine to work below the optimal level. So what you can do is to correct for these non-adiabatic transitions. So each time you have a transition that you don't want to have, you apply a term that brings it back to where it should be. And these techniques are called counter-diabatic techniques. So you just add an extra Hamiltonian to this one on top. Now this is proportional to sigma y. And the role of that term is, as I just said, to compensate all these unwanted non-adiabatic transitions. So in a sense, eliminate quantum friction. I'm not going to give you many equations. They'll be behind this exact formula. I'm just going to use a simple picture to give you some intuitive feeling how this works. So just imagine it's a sunny day, you're sitting in a cafe, and you order a drink. And now you have three options, actually. This is the waiter bringing you that glass, but he doesn't want to spill it. So one option is to move adiabatically slowly. Then it's not going to spill anything, because each elementary step is going to be an equilibrium step. But you're not going to be very happy with that solution, because it's going to take infinitely long until you get that drink. So you're going to stay thirsty for a very long time. The other option is, that's the adiabatic case. That's the non-adiabatic case. The waiter runs to your table, spills half of it. So you get it in finite time, but you lose half of it. So you're not going to be happy either. So the third solution, that's the counter-diabatic driving, and most of the waiters hopefully do it intuitively. So you apply this extra counter-diabatic driving. In that case, you tilt the glass or the plate a little bit. You can run, so you bring it in finite time. You don't spill anything. It's the same adiabatic result, but in finite time. So you have a non-adiabatic driving, and this is this is counter-diabatic driving. And this is what has been implemented in the experiment. So that's the first experimental plot. So you see the energy which is stored in our battery as a function of the cycles implemented with the machine from 0 to 28. And let's start by looking at the orange dots. So this is without the shortcut. So the driver simply, the waiter simply runs, speeds half of it, half of the gas or even more. And that's what you see here. That's after one cycle. That's after 28 cycles. So if you imagine you have a classical machine, think about your thermodynamic lectures. You start at some point, run a full cycle, and then you end up at the very beginning. And because you have no correlations between one cycle and the second one and the third one, you can repeat it many times, and the result is simply n times what you get for one cycle. So this is the dashed orange line. Now you do the same quantum mechanically with that experiment. You measure stroboscopically the energy stored in the battery, and as predicted, you see some very nice oscillations, and you conclude that these oscillations come from intercycle coherences, and that's exactly the case. We did some simulations looking at the off-diagonal matrix elements, and you exactly see the same oscillations. So these oscillations that you see here, stored in the battery, reveal the presence of quantum coherence, quantumness. Now you apply your counter-diabatic driving. So these are the green triangles. So by doing that, you're going to reduce quantum friction. So you expect things to be better, and this is indeed the case. if you look again after the first measurement, the classical result is this green dashed line. It lies above the orange one. The slope is higher, so you reduce friction. You deposit more energy into the battery. That's fine. But now look at these green arrows, triangles. You still have the oscillation, so it's still quantum, but every single one of them lies above the classical line. What do you conclude from that? Oh, it's very late. Every single quantum point is above the classical prediction. I do better than the classical machine. This quantum engine outperforms the classical counterpart. I have quantum advantage. It's kind of nice, right? It's a very nice, to my knowledge, for quantum heat engines, the first example where the quantum one outperforms the classical one. That's quantum advantage. Now let's move to the second topic of my talk, energy efficiency. A broad definition of energy efficiency is to say that you have an improved usage of available energetic resources. Right? You have some environment out there, you want to convert part of it into useful work, and you want to do it by losing as little as possible. So you get more for a similar input. And there's a whole revision on physics on that. So this is clearly associated with the energetic cost of this shortcut, right? So moving the plate for the waiter, yeah, sure, it's almost for free, but it's never for free because you have to do something. So applying these counter-diabatic techniques or these shortcut to diabaticity techniques, as they are called, cost some energy, so they're not for free. So we need, in the experiment, to evaluate the energy of this external driving, of this additional driving. And it's actually not that difficult as it sounds, because the PhD students control what happens to the machine by applying some external lasers, and they know the frequencies of these lasers. So they can actually evaluate, I mean, they know what they do, hopefully, and they can use that information to evaluate the cost. So one cost of this shortcut is to measure the change of the frequency that you apply to your system without the shortcut and with the shortcut, and then you want to normalize it with what you do without the shortcut. So this is the non-adiabatic without any shortcut, and this is with the shortcut. And then we compare that quantity with the amount of work, or the relative increase of work that you store into the battery. That's, let me repeat that one more time. The only thing which is measured is the amount of energy which is deposited into the battery. That's the load. And that's the result. My first reaction when I saw that plot is, why are the error bars so huge suddenly, right? It's the same data as here. The error bars are very small, and now they are, boom. Any answer to that? Is there an experimentalist in the room? There are experimentalists in the room. It's just error propagation. You have a quotient, and if you calculate that, it becomes much larger. So it's the same data that didn't get worse. They are as good as before, but now they're significantly larger. But still, let's look at the mean. So what you see here is the increase of work output as a function of cycle and the number of cycles. And you see that it's about 18% increase on average. The maximum value is here, 33% increase. So that's how much energy we extract, or the machine produces more by applying this shortcut. Now the cost of the shortcut, the energy cost, is this green line. There are some error bars there, but they're so small that we actually don't see them. The important thing to notice is 5% is here, so it's about 3%. So let me just stop with that for 1 second. You put 3% more energy into your system, and you get almost 20% more out of it. That's not bad, right? That's energy efficiency. And it's, in a sense, the shortcut works as a quantum lubricant. You just put a few drops of oil, and then you use less fuel, and that's why you save money at the end of the trip. So now that's the second aspect of the experiment, right? We had quantum advantage a few seconds ago, or minutes ago, and now we have energy efficiency. And we're able to combine the two aspects. I showed you everything as a function of the number of cycles. I could do the same by fixing the number of cycles by being 15, and now plot it as a function of the cycle time, just to be able to talk about power. So let's assume we start here, and we reduce the cycle time. So you reduce the number, the time you need to close a cycle And by doing that, as you expect, you increase the power of your machine. And again, you see the same two colors as before. That's without the shortcut, that's with the shortcut. And you immediately see if you add a few drops of lubricant, you get more out of it. So the power increases with the shortcut protocol. And the same question as before, how much does it cost? The same as before, right? So that's the power now. The increase is between 7 and 33%. Again, it's almost 30%. And the increase, the faster you drive, the more energy you need to reduce this unwanted adiabatic transition. But the increase is almost nothing, from 2.7% to 2.9%. It's, again, almost nothing. You add a little bit, and you get way more out of it. And that's already the conclusion, right? So I presented a single ion quantum engine coupled to a quantum battery. We only measured the battery. By seeing these oscillations, we can conclude that actually we have intercycle quantum coherence in the quantum machine. And then we suppress quantum friction, observe quantum advantage, evaluate the cost of the shortcut, find it's almost nothing, 10% of what you get out, that's efficiency. And I think all these points taken together, it's the first experimental observation of it, of quantum advantages combined with energy efficiency and shortcuts for full cycles. If you want to know more, ask questions or please check that reference.
Questions?
Thanks for the interesting talk. So I have one question. I assume that the advantage that you mentioned, so these oscillations come from developing correlations between the system and the battery over time.
From one cycle to the other, yeah.
But my question is, so why a classical system cannot also develop classical correlations between the system and the battery? So here you're assuming that the classical case is just uncorrelated, right?
Yes.
But I was wondering.
I don't assume that it's uncorrelated. Just imagine, take your car engine, right? You start. You run the cycle and you have the explosion, ignition to start again. And now you're trying to argue that between this first classical cycle and the second classical cycle, there should be strong enough coherences to be able to see oscillations. That's the line of argument that you.
No, I was wondering if you consider, I don't know, perhaps another more complex battery interacting with your system. Perhaps you still keep some time correlations over time, no? Or I mean, so I cannot see why this is excluded. As I think perhaps in typical machines that does not happen, but.
Actually, if you check that theory PRL, they compare that with the classical case, and you don't see the oscillations. And they try to argue in a very general way, for instance, by applying a force, which is a classical force, which is periodic in time, and you don't see it. Well, we can discuss it afterwards if you want to, but it's a quantum signature. That's the claim.
Okay. Thank you very much.
Felix. Oh, sorry, I'm not the chairman. But
Can you measure the coherence in the experiment directly?
Of which coherence? The one in the battery?
Which is the one that matters in the battery directly, I guess.
We have, yeah, you can, but then you need to do tomography. But they didn't want to do that because it's highly time consuming. There were many levels, but I can show you numerical simulations of the experiment that you always see. I never talked about these solid lines, but these are theoretical simulations or simulations of the experiment, numerical simulations that agree quite well with what is observed, and we did the same for the coherences, the off-diagonal matrix elements, and they exhibit exactly the same oscillations with the same period. That's the supplementary material of that paper. But measuring, yes, in principle, but the students don't want to do it.
Another one, maybe? Last one?
I have one last question before.
Well, thanks again for the talk. When you mentioned the difference between with and without shortcut, the figure of merit that you exposed was the difference between the average frequency. Why is that? I mean, why is that a reasonable field of merit, because when you end up your protocol, you have this exactly the same Hamiltonian, don't you? I mean, you should recover the energy.
But this omega is just the prefactor of that term. So this is Hamiltonian. If you change this omega, you change the energy. So this is the measure. This is the motivation. But you're right. There is not a unique quantifier of the cost of a shortcut. And there are many. And I never talked about these insets. What you see here is the variance, so the fluctuations of the work. And when you apply the shortcut, you increase them. And the question is by how much? And then you see that you increase them by 4 or 5%. It's always the same. And actually, the general argument is this term. Where is it? This term here is about 1 to 2 orders of magnitude smaller than the Hamiltonian. So whatever measure you want to choose, you're going to find a result, a cost for the shortcut, which is about 10 to 100, well, let's say 50 times smaller than the energy of your system. So it's always going to be much smaller.
Okay.
So that's it depends on the measure, but since it's so small, you don't care.
Okay,
Or you don't
thank
care.
you.
It's the same.
Thank you very much.
You're welcome.
Okay, I think we can close the session and thank all the speakers.
Thank you, everyone. Thank you to our chair, Victor. The day is over, so we'll see you tomorrow at 10 for a lot of nice talks. Have a good evening, and see you tomorrow.